Hello everyone, my name is Yunlei and I work at Alibaba Cloud Log Service team. Today I will share the petabyte scale log data analysis at Alibaba Group. And I will share our experience with Presto and the challenges we faced and also the optimizations we did for Presto. So today first I will give an introduction about our team and talk about the motivation why we provide the analysis service for logging data. And then I will talk about the challenges we faced. And after that, I will share our architecture to achieve scalability. And also share some ways to achieve low latency and high QPS or high concurrency. And after that, I will talk about some additional work based on a scalable framework of Presto. And finally, I will talk about the future roadmap. So first, let me introduce my team. And this may help you have a better understanding of the background and the motivation of why we provide the analysis service for logging data. And we are log service team, and we want to provide a service of being the infrastructure of all kinds of logging data inside Alibaba Group. For example, Linux server, mobile phone, web page, or Kubernetes. And all this data from the different kinds of platforms are collected to our clusters in real time. And then the consumer can consume the streaming data in real time without worrying about different platforms. And after that, we want to provide a service that as if people were operating their log file in a Linux server. For example, we notice that engineers often use the command grep to search some keyword from the log file. So in order to provide the real-time interactive search, we build the inverted index for log data. And by using index, people can search from the large amount of data with very low latency. And after that, we notice that in this era of data explosion, even the search results may contain thousands to millions rows, even to billions rows. That is a large amount of data. Even thousands of data is still a large number for human's eye, because people can't see all these logs line by line. So it is not easy for us to fully understand what is really happening inside the large amount of data. But if we can summarize data, for example, do some aggregation on the data. Take web access log as example. And if we can calculate the max value of the response time or average value of the response time, then we can be sure that we have a better understanding of the whole data. And so that is the motivation why we provide the analysis service for logging data. And we also provide the visualization service to visualize the interactive query result. And let me help people have a better understanding of the data trend. And so, in summary, my team provides a service of multi-tenant interactive analysis service for petabyte scale real-time log. So what's the challenges we faced? The first challenge is that high QPS. Every day we process about 400 million queries per day. And at the peak hour, there are about 10,000 queries running concurrently in one cluster. And every day, Presto processes about 1 quadrillion rows, and that is a huge number. Even though the data size is very large, but we can deliver our service with very low latency. The average latency of the interactive query is only about 500 milliseconds. So how do we deal with these challenges? How do we achieve the low latency? And in the later slides, I will talk about some techniques we used to deal with these challenges. In order to provide the service of interactive analysis, the first thing I did is introducing the Presto into our system. Many people ask me the question that why did we choose Presto in the first day? Well, I think that the first and most important reason is that Presto is really fast. It is flexible for interactive query. So it suits our use case. And Presto also has a scalable framework. We can develop our own connector, our own function, or optimizing rule. So it is easy for us to integrate Presto with our own storage. And also, the architecture and the coding style of Presto is very elegant. And the architecture is very simple. So it doesn't rely on any external components for deployment. And the coding style is also very simple. It is easy for us to learn about the internal implementation of Presto, and also easy for us to do modification for optimization. So that's the reason why we choose Presto in the first day. In order to deal with a large amount of data ingested per day, and every day there are about tens of petabytes of data ingested into our clusters. And data are collected from different kinds of platforms by SDK or agent. And data is sent to our clusters, and in the backend, the network keeps building inverted index or column format data for the input data. And then is stored in a distributed file system, which is called Pangu. And this storage is deployed in the same cluster. That's the inflow of the data ingestion and storage. When submitting a query, people use SDK or JDBC client to send their query through our front API server to one coordinator. We support distributed coordinators, and I will talk about the detailed design of that. In the backend, the Presto server reads both inverted index for filtering and column format data for computing. This is the flow of querying, and Presto plays a key role in this architecture. So how to support querying large amount of data? Every day we are processing about 1 quadrillion rows. And fortunately, Presto is a pure computing engine, so it is easy for us to decouple the computing and storage separately, so that we can scale Presto horizontally. And also, log data has a feature that it is immutable after ingested. And in the backend, we keep compacting a small file into a larger file. And when the file is large enough, it becomes immutable. One immutable file contains tens of millions of rows. So each time when we schedule a file, we schedule each file to one Presto server. And by this way, we can use a lot of Presto server for one query. And thus, it is helpful for us to query large amount of data. And the performance is very significant. If we run a simple group by query on 200 billion rows, it only takes about 20 seconds. And that is a large amount of data. And the latency is acceptable. So, how to achieve the low latency? We use a few techniques here. The first is the column format data. In the backend, we keep building column format data for log. And we all know that the column data is helpful for us to reducing the data size to read from disk. And it is also helpful for regularized execution. So it will make the query faster. And another thing we use is data locality. We all know that the network speed inside the same cluster is much more faster than the network between two clusters. So we deploy the Presto and the storage in the same shared cluster, and so that the data can transfer very fast. And we schedule a file every time when we schedule a file, we choose a free node by the order of machine, rack, and cluster. And another technique we use is cache and inverted index, and I will talk more detail about that. We all know that cache can make a query faster, and it is also helpful for us to remove some duplicated computation. And in order to take advantage of the cache, the scheduling algorithm must remember the scheduling history in memory. And every time when we schedule a file, we schedule each immutable file to the same node that it has ever been scheduled before, unless the workload of that node is much too high. And in that case, we will choose another free node. So there are 3 layers of cache: the row column data cache, and the intermediate result cache, and the final result cache. The final result cache and the raw data column cache are common solutions, but the intermediate cache is a very rare solution. So I'd like to talk more detail about intermediate cache. As I mentioned earlier, that file is immutable. So every time when we schedule a file, we schedule each mapper with exactly one immutable file. Then, after finishing the partial aggregation operator, we store the result of the partial aggregation operator in memory. And the next time, when you run exactly the same partial aggregation operator on exactly the same immutable file, then we can just read the result from the memory and send the intermediate result to final aggregation operator directly, without reading data from disk and recomputing the partial aggregation operator. We know that the partial aggregation operator deals with large amount of data and only generates small amount of data. So most of the computing happens in the partial aggregation operator. And by this way, we can achieve a faster query. And also it will save us a lot of CPU and I/O resources. So what's the performance of cache? Every day, there are more than about 100 million queries hitting final result cache. And the average latency when hitting final result cache is only about 6 milliseconds. So it is really fast. And what's more, the final result cache can help us prevent a lot of duplicated computation and save us a lot of resources. And what about the performance of intermediate cache? For 1 billion row, it only takes about 1.3 seconds when hitting intermediate cache. But it will take about 3 seconds when not hitting the intermediate cache. So the comparison of the two latency is very impressive. Another technique we used is inverted index. In the first day, we just used the inverted index for searching data. And after introducing Presto in our system, I pushed down predicates from the Presto to a storage layer. And then use the inverted index to first calculate the matched row ID. And only use the matched row ID to read from disk, read the column data, and send the matched data to Presto. And this strategy is very effective if we can use index to skip some file or read only a small part of the file. This will save us a lot of I/O resources. And if you run a query, select count star, that will be extremely fast because we can use only index for computing. Every day we are processing about 400 million queries, and the main challenge is on coordinator. This picture was taken about 2 years ago, and at that time there is only one single coordinator. This shows the top 4 nodes with the highest CPU usage, and the first picture is the coordinator. You can notice that the CPU usage of coordinator is much higher than normal worker. And in our cluster, one single coordinator can only process about 1,000 queries running concurrently at the most. So the single coordinator is the bottleneck of the whole cluster. It has a problem of both scalability and availability. So in order to improve the performance of coordinator, I did a few things. First is support the distributed scalable coordinators. And another thing we did is transfer the query result from output stage to client directly without worrying coordinator. So let's look at the detailed design of the distributed coordinators. And I designed the distributed coordinators for scalability. And there are two kinds of roles in this design. The first is a global coordinator, and the second is a distributed coordinator. The global coordinator has only one instance. It is responsible for cluster management. For example, detect node state and replicate all node state information to other coordinators. And also track memory usage and assign the largest query to the reserved pool. And the distributed coordinators are responsible for query management. For example, pass the query, create a logical plan, optimize logical plan, and schedule task, and check the task state. It is also responsible for a user queue. Every time when submitting a query, the user selects one coordinator to send his query based on the hash of his username. In this way, the queries belonging to one user can always be found in one coordinator. We can notice that this design is not 100% perfect because the global queue is not supported, but it is enough for our scenario. It helps us to scale the coordinators horizontally for much higher concurrency. Another thing we did is optimizing the data transfer. And in the original design, the coordinator transfers data from out of the stage to clients. So the coordinator will have to serialize the query result to JSON format. And that we will know that the JSON serialization is very slow. So what about if the coordinator transfers large amount of data, for example, 1 GB of data? That will take a lot of CPU usage of coordinator. So in order to improve the performance of coordinator, here is my solution. The coordinator will tell the client all the addresses of the output stage because there may be more than one node in the output stage. And the client will use addresses to talk to the output stage to directly fetch data with proto buffer format. By this way, we can make the query fast and also save a lot of CPU usage of coordinator. So, in summary, we did a few optimizations, and here is the final performance. We supported distributed coordinator and optimized the data transfer so that we can achieve every day we can process about 400 million queries. And we decouple the computing and the storage layer to support querying large amount of data. And every day we can process about 1 quadrillion rows. And we use the column storage, data locality, cache, event index, so that we can achieve a much lower latency. Every day the average latency is only about 500 milliseconds. Besides those optimizations, we also did a few additional work based on the scalable framework of Presto. The first thing we did is we developed a machine learning library for time series data. And also we noticed that only log data is not enough for analysis. Sometimes we have to join the log data with some external data. So I developed a command to read object file on OSS storage. And we also use Presto as a federated SQL engine. We push down a Prometheus to Prometheus to query the data on Prometheus. In the future, there are still a lot of things to do. The biggest challenge is still on coordinator, and I will keep optimizing the performance of coordinator. And another thing we want to do is to increase the availability of discovery. By now, it has only one instance. And we also want to improve the performance of data exchange efficiency with RPC protocol. And it will help us to shuffle large amount of data. So I have finished my presentation. If you have any question, you can ask me in the QA session or contact me by email. Thank you for your time.